Okay, so far we have introduced the idea of E and reviewed properties of logarithms and exponential functions, that kind of thing. This idea of the number E, which turns out is a really big deal in exponential functions. And also, we saw yesterday how um, interesting and useful it is in calculus. So, we did yesterday, we did derivatives of exponential functions. And don't forget, and I tried to make a big deal out of this yesterday. Yes, we focused a lot on exponential functions where the base is this special number E, because that's a lot of what we are going to be doing. But don't forget, we have also learned um, derivatives of exponential functions with other bases. So base 2, 3, 10, whatever, right? And taking the derivative of those functions is something we need to know how to do. And just to be careful, because we don't do it as much and it's got a little extra to it that you have to remember. And you don't want to forget that. And we're going to see a similar thing happen today. So after hopefully these 2 days, you will have um, uh, seen it enough that you'll remember. And all I can say is, stress to really do the practice and just remind yourself of those special cases, because they won't come up after today for a few days while we're graphing. They won't come up at least very often, if at all. And but they will be on the test. And so you just have to remember that extra little constant in there. So what were the derivatives that we looked at yesterday? We did d by dx of e to the x. Does anybody know what this one is? Going once, going twice. The easiest derivative in all of calculus, I would say. Maybe derivative of a constant is easier. It's just zero. I don't know. But this one's pretty famous, so that makes it easy. And then d by dx, this is the trickier one. Any other base, or any base, even e, it has this extra constant, and if it's base e, that constant is 1. Okay. This first part is the same, b to the x, right? But we add in this constant, and um, again, it is important to know that that is a constant. B is not something that changes. B is the base, so it would be given. It would be 2 or 3 or e, possibly. And if it's e, this is ln of e, and ln of e is 1, right? Ln of e, so I have to do an exponent to the 1, is 1. So in this case, my constant is 1. And so in this case, sorry, my constant is 1, and so we don't write it. We just ignore it, right? But this is what I'm talking about. Whenever we have another base, be careful that you remember that part. And then more often than not, we're actually doing something like this, where u is some other function. And so this part is easy, but then times u prime. That's not u to the 1, that's u prime, right? So it's e to the u times the derivative of u. And then same thing, d by dx of e to the, b to the u, sorry, equals b to the u times ln b times u prime. The order of these doesn't matter. It's not going to be right or wrong. Multiplication order doesn't matter. That's just the habit that I'm in, that I tend to do it. Some people might want to put ln b at the end because it's a constant and just keep it at the end. But if you do it at the end, just don't forget about it. All right, now find the derivative of y equals ln of x. Yeah, go for it. What do you think? I would encourage you to pause the video here, think about it for a little bit. What could you try? What could you do? You have all the skills so far already from this course to be able to figure this out yourself. It's not even that hard, but it's novel. It's new, right? And then that's the part that's hard, is coming up with a new idea, starting from nowhere and knowing what to do, or being willing to try something. That's the hard part. But the actual computation, the actual steps to this are not going to be that hard. So I would encourage you to pause, Give it a try. See if you can even think of what you might do. First thing you might try is remind yourself of what ln actually means and rewrite that. So it means log base e of x. So again, you can pause and see if you can think of what to do next. Trying to think of what to do next is a great challenge, and it's a great skill, similar to trig identities, where when you don't know what exactly is the right thing to do, and you ask yourself, well, what can I do? I don't, and this is part of the problem, is we often strive to, when we're solving mathematical problems, to know what the next step is, right? And in fact, your teachers will often advise this to you. You need to know what, you don't want to be guessing at what the step is, you want to know what the step is. But the next step of, the next level of mastery of mathematics is when you don't know what to do and you have to figure that out, and you have to, and that's just becoming a good problem solver and knowing what to try. So something you could try here is rearrange this, write it in exponential form. Why is this useful? Well, we know how to take the derivative of that, don't we? I mean, that's what we learned yesterday, taking the derivative of exponential functions. So why wouldn't I take something that I don't know how to take the derivative of and turn it into something that I do know how to take the derivative of? That's a great idea. This is going to be implicit differentiation because I'm going to be taking the derivative of that. So this is e to the y times the derivative of the exponent. What's that? dy by dx equals derivative of x is 1. Now what do? Well, I have to solve for dy by dx. So dy by dx equals 1 over e to the y. That's implicit form, which is what we've always done. What if I don't want to leave it in implicit form? How can I rewrite this in another way that might be more useful? What's another way of saying 1 over e to the y in the context of this question? E to the y is x, so 1 over e to the y is 1 over x. And we're done. There's your derivative. And now you see what I mean about how simple those steps are. Not one of those steps is overly complicated. It's just knowing to do those steps. It's knowing what to try, what to start with, and how to proceed. So to summarize, d by dx of ln of x is 1 over x. Again, I said this yesterday, pretty simple, not quite as simple as exponential, but very simple, okay? And d by dx of ln of u, what do you think that is? 1 over u times u prime, or u prime over u. And you can do it either way. Some people might like to do it in separate parts and simplify after if you have to simplify, right? Like just focus on one thing at a time, and that's fine. But some people are going to want to go straight to a more simplified version. And of course, either of those is fine. All right, let's try some examples. So y prime, 1 over the argument of the log or the ln times the derivative of the argument. So the derivative of 2x squared plus 3x minus 5 is 4x plus 3. And of course, you're not going to get marked wrong for leaving it like that, but generally speaking, we're going to aim to write it like this. Now, after the video from the first day of this unit, so a couple of days ago, I realized that I forgot to mention something kind of important. The title of the video, or the title of the lesson, in fact, here it is, was the natural logarithm, and Unit 5 is called the natural logarithm. And I didn't even mention that, whoops, I didn't even mention that once, why that was the title, okay? And maybe you figured that out, but the reason why that was the title is when we have log base e, what that means, sorry, log base e of, let's say, x. That's the same as ln of x, right? And that's what we talked about. And that is what the natural logarithm is. The natural logarithm is base e, and we call it ln. And so whenever you hear that term natural logarithm, that's what it's referring to. And I did touch on this, that it's kind of known to be the natural base for exponential growth, and by the same token for logarithms as well. It seems like exponential growth kind of always simplifies to the natural logarithm, to base e. So that's, makes sense that we would call it that. But I realized that I don't think I actually pointed that out. So I did want to make explicitly state that that's what the term natural logarithm means. Okay, let's try another one. Okay, so the logarithm base e with a square root as the argument. Okay, so y prime equals 1 over the argument times the derivative of the argument. So again, this is 2x. Hopefully we've kind of mastered this by now. 2x to the 1/2, so the 1/2 comes out front, times 2x plus 7. Subtract 1 from the exponent, so that's negative 1/2, times the derivative of what's inside, which is 2. Hopefully you notice that those multiply to 1, and I get 1 over root 2x plus 7 times, well, this is 1 over square root of 2x plus 7. So how can we simplify that? 1 over 2x plus 7. Interesting. That's not a rule. Please don't think that that's a rule. That's a rule because the derivative of this canceled the 1/2. Okay, otherwise it wouldn't quite look like that. It wouldn't be quite that simple. Okay, this part would have still occurred and would have still simplified, but there's no rule that whenever you're doing a square root, it works out to that. Okay, don't make up your own rules. Now, as often is the case with logarithms, there are different ways of doing these. Okay, by using some of the logarithm properties. So what if I did this? Y equals ln 2x plus 7 to the 1/2. What if I wrote it, the square root, in exponential form? Who can think of what we could do with that? Great thing about logarithms is it allows us to take those exponents out front. Okay, and now I can take the derivative. Times the derivative of the argument. Once again, these multiply out to 1. Now, my first one was 3 steps. Maybe you could have skipped that step, I don't know. Second one looks like 4 steps, but I certainly could have skipped that step and gone straight to this. Okay, whoops, what happened there? So it's up to you which one you think is better. Oh, I erased a whole bunch of stuff. It's up to you which one do you think is better. To me, this one's a little bit simpler, less likely to make a mistake with the square roots, that kind of thing, but entirely up to you. But look for those moments where you have exponents and they can come out in front, and that can often make a question more simple. Remember, efficiency and proficiency is key. Determine the location or locations where the slope of the tangent line would be horizontal for the curve below. Y equals x squared times ln of x. What's the first thing you notice about this? So all we're doing is finding the location where the slope of the tangent is horizontal, not finding an equation of a line or anything like that. Product rule. Very nice. So y prime equals derivative of the first thing times the second thing plus derivative of the second thing. That's easy. It's just 1 over x in this case times the first thing. Y prime equals 2x times ln x, and x squared divided by x just gives me x. Okay. Tangent line horizontal means what? Means slope is 0. So how are we going to do this? Aha. This is where solving logarithmic equations comes into play. This one's maybe a little bit different from ones we've seen. But it's not too tricky. It's something I think that we can do. And this is the kind of thing where when we're sketching, we're going to be doing it a whole bunch of times, right? Okay, so maybe you see what you have to do here. And it's factor out an x. Whoops, 2 ln x, I just factored out that x, plus 1. Okay. So therefore, x equals 0, or 2 ln x plus 1 equals 0. Now let's think about this for a moment. What does this solution mean? It means when x equals 0, my function would have a horizontal tangent line. But what happens when I sub 0 into that function? 0 squared times ln of 0. Aha! You can't take the logarithm of 0. It is not in the domain. So this one's no good. So ln of x equals negative 1/2. So x equals e to the negative 1/2, which is 1 over the square root of e. If we wanted to write it with positive exponents or in radical form, nothing in the question said I have to, but it's a good thing to think about. If we had to use this for something, maybe we want this version, maybe we want that version. Who knows? Okay, so watch out for solutions that are outside of the domain of the derivative, but also outside the domain of the original function. Okay, if I plugged 0 into the derivative, it would not work because I would be taking the ln of 0 and that wouldn't work as well. Okay, so it wouldn't work in the derivative and it also wouldn't work in the original function. And that's something that we saw a little bit of or touched on in Unit 3 when we saw sort of where the derivative does not exist, but it's a vertical asymptote. So the function doesn't exist, but it's different here, right? It's not It really isn't the same as, doesn't have quite the same feeling as back then. Okay, so that's a little bit of that. Let's try some other different kinds of examples. Looks like we're mixing and matching a little bit here. You can pause and give this one a try and see if you can uh, get it to a point, and then we're going to talk about simplifying this one a little bit because that will be important for later. Okay, but the first line won't be too bad. So 1 over the argument of the log times the derivative of the argument, which is the derivative of e to the 3x is e to the 3x times 3, or 3e to the 3x, minus e to the negative x times negative 1, the derivative of the exponent. Okay, so I'm going to do two things here. I'm going to simplify this part a little bit, and I'm going to bring it into the top as well. So this is 3e to the 3x plus e to the negative x. And you could certainly have gone straight to this. I'm doing it slowly so people can follow along. But this is something that I could have easily brought the 3 out front to start, and I could have easily seen that the negative 1 is going to multiply with the negative to become positive, and I could have certainly put it into the numerator in the first step. Now, this is not necessarily the easiest thing to solve. We don't like negative exponents. How can I get rid of them? Well, what if I multiply by e to the positive x over e to the positive x? And if I had negative 2x, I would have to multiply by e to the positive 2x, right? Or x squared, negative x squared to the positive x squared to get rid of that, right? So this is going to multiply into both on top and both on bottom. So this becomes 3e to the 4x plus 1e to the negative x. I'm going to do this over here. E to the negative x times e to the positive x is e to the negative x plus x, which is e to the 0, which is 1. And that happens to work out on the bottom as e to the 4x minus 1 for the same reason. This cannot be simplified because I'm also adding and subtracting. Possibly other cases you would be able to, but generally speaking, that's as far as we can take it. Okay. That's going to be a lot easier to solve if I'm sketching or determining where the derivative is equal to 0 or where it does not exist. This is going to be a lot easier than that. Here's another one. What do we notice about this? Once again, product rule. Derivative of the first thing is e to the root x times the derivative of root x, which is 1/2 x, x to the negative 1/2 times, how about I bring that 2 out front, 2 ln x plus derivative of the second thing, 1 over x squared times the derivative of the argument, which is 2x, times the first thing, e to the root x. So let's see, I've got a 1/2 and a 2 all multiplied together, so they will turn into a 1. So this looks like e to the root x times ln x over root x plus 2. So I've got an x squared and an x. That will simplify. So 2e to the root x over x. If I had to take this further, I would multiply this one by root x over root x, which would give me a common denominator, and I could then put them together into 1, and then I could factor out an e to the x. But it doesn't look like I'd be able to do a lot more. This would probably be tricky to solve if I was setting it equal to 0 in the end. So some of these ones aren't going to simplify. They're going to be first line only. They're not really going to simplify nicely or go any further. So we're just going to leave it like that. Okay. Okay, differentiate each of the following with bases other than e. Well, we haven't actually even talked about this. So first of all, we need to know what the rule is, d by dx, and it is similar to to exponential functions. D by dx of log base b of x equals 1 over x ln b. So the trick is the ln b is in the denominator this time. And d by dx of log base b of u is equal to 1 over u ln b times u prime, or u prime over u ln b. Okay. This is from yesterday. Y prime equals 3 to the 2x times ln of 3. Sometimes putting that in brackets makes it clearer. Times 2, derivative of the exponent. Okay, and you're done. Similarly here, y prime is 1 over the argument times ln of the base times the derivative of the argument, which is 4x cubed minus 6x. Brackets around all of that because otherwise it looks like times 4x cubed and then just minus 6x, but it's times the whole thing. And again, generally we are going to want that on top. Something like that. Okay, go ahead and give this one a try. Pause the video and give it a try, at least the first line. It is indeed product rule. So derivative of the first thing. Times ln of the base, 8, times the derivative of the exponent. All of that times the second thing. When in doubt, use brackets around arguments, use brackets around things like this. If I wrote this ln 8 for x, that is definitely not clear what the argument is. Of course, I could put brackets around the 8, or like I did here, I could put brackets around the whole thing, maybe even a little bit better. I don't know, but it's maybe depends on your handwriting. It's up to you, but make sure that it is clear. You've seen this lots of times before, kind of like I talked about in this one here. If you don't have brackets around a sum or a difference, you will lose marks. It is not clear what you are multiplying. Okay, plus derivative of the second thing, 1 over 4x times ln of the base, and the 4x is the argument of the log, right? So it's just 1 over that times ln of the base times derivative of the argument, which is 4, times the first thing. These 4's simplify to 1. So I don't think there's much I can do to simplify this part. Ln of 8 times 4x times log base 5 of 4x plus 8 to the 2x squared over x ln 5. This isn't going to help much, but it is something that you always want to be aware of, that that exponential part could factor out if for some reason I wanted it to. Let's see what happens in this case. Ln of 8. Actually, I'll do it this way. 4x ln 8 times log 5 of 4x plus 1 over x ln 5. That really doesn't help much because that is not something that looks like it's going to be easily solvable. So pulling the 8 to the 2x squared out front probably didn't help much, but that just often happens, right? When you're doing exponential stuff, it often happens that that exponential part will factor out because of the nature of their derivative. Okay, one more. There's a trick to this one. This is log base 10. Aha. So it would be 1 over the argument, which is a fraction, which is nasty, times a ln of 10 times the derivative of the argument, which would be quotient rule. Does anybody see an easier way to do this? Aha, log properties. Log of x plus 3, that argument has to be in brackets because otherwise it would be log of x plus 3, right? Minus log 7 minus 2x. Oh boy, this is a lot easier. 1 over x plus 3 ln 10. Done, because the derivative of x plus 3 is just 1. Minus 1 over 7 minus 2x ln 10 times negative 2, which equals 1 over x plus 3 times ln of 10 plus the two negatives turn into a plus 7 minus 2x ln 10. Yes, the ln 10 on the bottom of both could factor out. It's just a constant. I'd be factoring out 1 over ln 10, but it's just a constant, so I'm not sure how that would really help. Again, cleaning this up, well, it wouldn't be that bad. This is just a number. So maybe if I was going to clean it up, I would factor it out front, but then I would just get a common denominator between these parts. And that would be something that we do know how to solve, so it might not be too bad. But we're not worried about that right now. But keep in mind, it is useful to remember that the ln of 10 is, that part of any of these functions, the ln part, is a constant. It's not something that you're setting equal to 0 to solve, right? It's just a constant. So that is derivatives of logarithmic functions. Specifically when we do base e, which is when we have the natural logarithm, or ln, and we saw the derivatives of those and did some different kinds. The one where we found the location where the slope of the tangent was 0. But then again, the ones that are going to be less common moving forward in this unit, because we're going to be spending a few days on sketching coming up, but the less common ones where it has a base other than e. And we did a little bit of reviewing of the stuff from yesterday where we mixed up some of the exponential functions with the logarithmic functions, which is good practice. Okay, so now we have seen how to find derivatives of exponential functions, how to find derivatives of logarithmic functions, reminded ourselves of the logarithmic properties, and we've already started to use those properties of logarithms and really see how beneficial they can be and how useful they can be to the kinds of to even finding derivatives and making things easier to find derivatives. And as we've said so many times, it's all about efficiency and all about not just speed, but making your life easier so you're less likely to make mistakes. And if you're sketching or doing any other kind of question like that, having it in the right form, an easier form to set it equal to 0 and solve is going to be key, right? So keep that in mind as you're doing your practice, that there are going to be that it's not always about right and wrong, but there are going to be little tricks or little things to observe along the way that are going to make it easier and going to not just take the derivative easier, but any next steps you're going to be doing with the derivative possibly make them easier too. Okay, good luck.